and people want to find resources to exploit. And yeah? Right, so if you're somebody who owns something and you're hiring somebody, that's true. But I'm talking about just my own effort. I'm moving in and I'm trying to. So that would come into it. But we're just keeping the situation fairly simple now. Yeah? Yeah, the cost per effort would go up. But let's say there are a number of opportunities like this, and they would be dynamically adjusting, and the C's wouldn't be constant. But for that moment, let's say with a lot of situations like this, what happens is I choose the best one, and more people come in. And at any particular point in time, there is a cost and there is a price. And what's going to happen is in a highly competitive situation where more and more people are looking for opportunities, the resources are going to be driven down these curves, or the costs are going to be driven up, so these are going to become steeper. But basically, I will go into resources and have an opportunity to exploit it as long as I can make a profit. So what happens is, in this whole big situation, with different opportunities, in each of those resource opportunities, whether the green curve moves up or this curve changes, what's going to happen is that effort is going to come in closer and closer to this point. One thing's for sure is that it can't go beyond that point. That's not sustainable. If I'm exploiting a resource and it's costing me more than I'm getting out of it, then I'm going to go bankrupt. Yeah. Yeah. Okay, so can you say that a little more simply?
Yeah, like if you have fixed costs
yeah.
that are going to be there whether you choose to keep fishing or not,
yeah.
then you might as well keep fishing even if your return for one is not.
Even if it's negative?
Yeah, right.
Well, if it's negative, you're going to have to keep paying out. You've got some capitalization until you draw it down and then you're finished.
So are you still covering your variable costs? I mean, fixed costs?
Well, so it is a very complicated argument. But in 1951, 2, 3, 4, when Monroe wrote a paper, what he argued is that there is some variation among individuals. Those individuals that are least able, when you're operating in a region around here, some individuals make a profit, some individuals make a loss. Those who make a loss drop out first. But what he argued is that there is an equilibrium called the bioeconomic equilibrium. It's called bioeconomic because it's a biological equilibrium because we're talking about sustainability, and it's an economic equilibrium because if you're on one side of this, you go to that point, you head up towards the point, because individuals making a loss or drop out, so on average, people are moving towards a net profit, but there may still be a loss because there are too many people in there and they'll drop out. Over here, when you have a positive return, individuals may move in if it's highly competitive and all other markets are they're all closing out. So he argued that in exploiting resources, resource exploitation tends towards this bioeconomic equilibrium point, and that's called that's called Gordon's principle. And so you can read the original paper, which I've given you at the site. So that's Gordon's principle. And when that V tends to this V infinity over time. And he says that if you're above here making a profit, more people will move in. If you're below making a loss on average, the least efficient will move out. So this is a very simplistic argument, and in order to understand it, and it's got much more structure to it. And to understand that structure, you have to look at the mix of opportunities that are available in the general economy and so on. But it's just this principle that exploitation of resources will tend towards effort levels that are at the bioeconomic equilibrium. On the other hand, so this is Gordon's principle, what we call for open access. So that's for an open access. Now, if you're a sole owner, now as a sole owner, you can make a decision on what your effort level should be. In Gordon's principle, you can't decide on what the effort level should be because the market decides. And under Gordon's principle, open market determines V, and here sole owner determines V. So you have this resource and you say, I'm going to maximize what I can get out of this resource. I'm going to turn that into cash, and then I'm going to invest my cash somewhere else, like in the bank or wherever. If I'm going to operate this fishery or this resource, why would I operate around here and make and get rent from it at a particular rate? I want to maximize my rent rate. So as a sole individual, you might want to maximize your rent rate. And when I say sole ownership, it may not be a single individual. It could be a consortium where people agree that they've each got some shares, and the shareholders say, let's maximize our profit. But it's not open to the market to determine what's going on. It's a group of people who come together to make an agreement. We'll own this together, and we'll make the best decision so that we can maximize our return. And so you have control over maximizing your return. So this is the sole ownership. So the sole ownership solution is to have a VMSR. Now, if you're a sole owner, you don't just want to maximize your return. You want to maximize your discounted rate of return. Because this return is return rate into the future. And you say, I'm going to get some dollars now, and I'm going to get some dollars next year, and I'm going to get some dollars 10 years from now. But the dollars 10 years from now are not equal to the dollars that I get now. So what I should do is I should write down an equation that solves what is called the net present value of the resource. So if you're a sole owner, if you didn't know about discounting, or if discounting was zero, you would go for your maximum sustainable rent solution. But if there's discounting, so with discounting delta, the net present value, or sometimes it's just called the present value, that's equal to, now this is the rate. That's the rate at which you'll get sustainable returns for some value of V. And if we want to maximize that rate, we go to the MSR solution. But now what we want to do is we want to integrate for all time into the future, starting now, I'll call now time 0. We want to go from time 0 to infinity, e to the minus delta t dt. So that's how we write that. And now if you want to solve this problem, what it does is it says, not only do I want to maximize the rate, but rather I want to also take into account discounting, which is that future dollars are worth less to me than current dollars. So I actually want to take out, I want to exploit it at a different rate so that I can get current value maximized over future values. And so this then is going to be a non-equilibrium situation. And the reason why this is a non-equilibrium, the net present value for the general equation, dx dt equals f of x minus, now I've been working with v times x, but actually I can write this more generally as h, a function of x and v, and then I can change this to h is a function of x and v. So this is my harvest rate. I don't need to worry anymore about an equilibrium situation, because when I come to a resource, I'm usually not in an equilibrium situation. I might have an unexploited resource, so I'm going to drive it to some equilibrium. What is that equilibrium I should drive it to? Should I drive the resource to the maximum sustainable rent situation, or should I drive it somewhere else? When you set up the problem like this, here's your present value that you want to maximize for a choice of v, and now you don't have to make v equal to a constant. You can make it a function of time as well, subject to this equation. So that's how you state the general problem mathematically. Now if the discount is very high, that means the delta goes to infinity, then you don't care about the future, and you want to just take out as much resource as you possibly can. And so what you do is you choose v, and you drive the population down to this point, and you take out as much as you can, as rapidly as you can of the resource, getting the maximum price that you can getting the maximum value here that you can, assuming that c and p stay constant. So this assumes that c and p stay constant. And then when you hit that point, it's over. But because the discount rate is infinite, you don't care about future value. You want to turn your resource as rapidly as possible into cash, and so you just use the biggest v possible. If the discount rate is 0, then you want to just maximize this over all time. And actually the integral in this case, when delta is equal to 0, is infinite. So this problem you can't really solve in this form. But you can show that as delta goes to 0, the solution will go to maximizing this term over here for all time, which is VMSR. But for some delta between 0 and infinity, you're going to be somewhere between VMSR. And so find V delta that maximizes this, and or find V of t that maximizes this. And it actually turns out that you're going to drive the population to some equilibrium, and that equilibrium is going to be somewhere between here and here. And I don't know where it'll be. It could be over here, or it could be over here. I'll just call this V subscript delta. When delta is equal to 0, I take V delta in this direction. When delta is equal to, as delta goes to infinity, V delta goes towards this solution. That's why I would call this V subscript infinity. Because the bionomic equilibrium turns out to be where you will drive the resource to if the discount is infinite. Maximum sustainable rent will turn out to be where you drive the resource to when delta goes to 0. But for some delta between 0 and infinity, what you're going to do is you're going to have a corresponding x delta that makes this equilibrium 0. So if you choose a V delta, then you can find an x delta to make this 0. And then what your solution looks like is you start out at x0. Let's say this is an unexploited resource. Now what you do is you harvest the population as rapidly as you can until you get down to this point. And then after this, so you apply V delta as your effort level over here, and over here you apply V max, which you're assuming is greater than V delta. So it says apply your maximum effort level, which is greater than your sustainable level, drive the population down to this point, and then sustain it there. And that's what the solution to this problem would look like. Now, I'm not doing the math for you, because the math is beyond calculus. It's called calculus of variations to solve this problem. And so if you're doing resource economics as a graduate student, mathematical economics, then you would solve this problem. But I'm giving you the solution here. But I want you to understand the different elements of the solution. Now, for this figure, there's a corresponding figure that contains all the x's. Just like up there, I had this diagram and this diagram. Over here, what I've drawn is that diagram, but there's a corresponding diagram where there's xMSY, xMSR, x delta, that gives you the equilibrium. And that diagram is given to you in your notes that I've given on the harvesting theory. So what I'm going to do is in your midterm, I'm going to say to you, and I'll give you the question that I'll ask, discuss the bioeconomic theory of harvesting by drawing this graph and the corresponding x graph and discussing each of the different quantities on that graph, like xMSR, VMSR, x infinity, V infinity, x delta, V delta, so on. So you have to read your notes and you have to kind of prepare for that. Yeah. Yeah, how all these arguments work. So understand that you have a graph on top, f of x, that tells you about the dynamics of your population and the equilibrium values. Over here, how that translates into a sustainable yield analysis. That is Gordon's principle that tells you that in an open access resource, effort level approaches V infinity because, and the reasons we discussed, that you can focus on sustaining yield, but in fact, you don't want to maximize yield, you want to maximize rent. And if you go for maximizing rent, then you get a maximum sustainable rent solution. However, if you take discounting into account, the actual solution, equilibrium, that you want to drive the resource to for sustainability is going to be somewhere between the bioeconomic equilibrium and the sole ownership equilibrium solution. And it's going to depend on delta, and you're not going to be able to solve it because you have to mathematically solve these equations. But actually, people have done this for the logistic model and different models. But you just have to know the concepts and not do the math. Okay? Yeah. Sorry? Where delta, yeah. Because it depends on the value of delta. If delta is close to 0, the effort level, the sustainable effort level will be close to MSR. If delta is very large, the sustainable effort level will go over to V infinity. So it depends on the value. If it's a small value, delta is equal to, just a fraction of a percent, then you can just worry about sustaining the rent. And if delta is very large, then you just turn the resource into money as fast as possible and then buy something that will hold its value. But actually, if delta is very large, so that's if prices are constant. If delta is very large, then the price is actually going to change as well. So the constant price assumption for large delta doesn't hold. But that's a level of analysis that we're not going to get into. These are to give you some of the basic ideas that people think about when they do resource economics, exploitation of sustainable resources. So what I'm trying to do here is to get you to expose to the notions of maximum sustainable yield, maximum sustainable rent, bioeconomic equilibrium, how discounting can affect the solutions. That's the basic idea behind this. And we've done it in a mathematical framework because otherwise it's just a bunch of words and you don't see the logic behind it. In a mathematical framework, you can see more of the logic behind it. Is that true? I hope so. Okay, thanks. Yeah. Yeah.
This one is 0, right?
This is always 0 because that's your equilibrium. That's how you find out what's sustainable. Things are only sustainable if you go to an equilibrium. But when you start out at a different place. So you might start out at the equilibrium, then you don't have to go anywhere. You stay there and everything. But when you start out exploiting a resource, usually it's not at the optimal place.
Okay. But solution for this
Yeah.
one is just this.
Well, the solution to this is going to look like this. Use your maximum value to drive your population to X delta, and then you apply V delta and you sustain it. And that will solve this problem where you have a constraint on the maximum value of, because you can't have an infinite effort. So you have some maximum effort that's possible for you to use. And okay.